Lecture 26 covers Section 7.3. At the end of today's lecture, you should be able to identify the difference between frames and trusses, as well as analyze frames using our equilibrium equations. A non-two-force body is referred to as a frame or machine. That is to say, at least one member of a frame or machine has more than two forces acting on it, or a combination of forces and moments. Frames are rigid structures, that is, they do not move, while machines are not. Machines rely on their supports to maintain their shape, and their shape can change based upon the magnitude of the force that represents their supports. We will decompose frames and machines into individual components and apply our equilibrium equations on a component-wise basis, which is the same solution methodology we used for solving statically determinate systems. Now note that frames are often made of contiguous members and not just two-force members, but they can also have two-force members within. Let us consider the following basketball hoop. If we have a force of 900 newtons applied at point F in the downward direction, we want to determine force F applied at point A for our basketball hoop to stay upright, as well as determine the reactionary forces and moment about point O for the system to be in equilibrium. The schematic of the basketball hoop is shown below. We recognize that if a system is in global equilibrium, each component also has to be in local equilibrium. Therefore, we will break apart this frame and analyze each individual component. We will start with the hoop and backboard. For the hoop and backboard, we have reactionary forces at points E and D, which represent the pins, as well as our applied force at F. We will begin by summing the forces in the x direction and setting them equal to 0. We have Rex plus Rdx being equal to 0. We will call this equation 1. Next, we will sum the forces in the y direction and set them equal to 0. We see Rdy, Rey, and 900 newtons all act in the negative y direction. Thus, equation 2 takes the form Rdy plus Rey plus 900 newtons is equal to 0. Lastly, we will sum our moments about a point. We see the lines of action of Rdy and Rey, as well as Rex intersect point E, and thus this is the most preferred point to take our moment about. Summing our moments about point E and setting it equal to 0, we see our 900 newton force acts on a moment arm of 0.2 meters, creating a clockwise moment, whereas Rdx acts on a moment arm of 0.750 meters, creating a counterclockwise moment. Thus, equation 3 takes the form 0.2 meters times 900 newtons is equal to 0.75 meters times Rdx. Next, we will analyze member ABE. Now, when analyzing member ABE, we have to be careful about the specification of our reactionary forces at point E. These forces must take the opposite direction as what was applied on the backboard at point E due to Newton's third law. Therefore, if we proceed with the summation of forces in the x direction and set those equal to 0, we find that Rbx is equal to Rex. This will be denoted equation 4. If we sum the forces in the y direction and set these equal to 0, we'd have Rby plus our applied force F must equal Rey. We'll denote this as equation 5. Lastly, we will take our sum of our moments about point E and set this equal to 0. In this situation, we have Rey acting on a moment arm of 0.5 meters, and our applied force F acting on a moment arm of 0.470 meters. These create a counterclockwise moment, which will be counteracted by Rex, which is acting on a moment arm of 0.266 meters, which is creating a clockwise moment. We will denote this as equation 6. Next, we will analyze member CD. Note that when looking at member CD, Rdx and Rdy will be acting in opposite directions than specified on our backboard. This is due to Newton's third law. Therefore, looking at member CD, we can sum our forces in the x direction, set these equal to 0, and we find that Rdx is going to be equal to Rcx. We will call this equation 7. Summing our forces in the y direction and setting them equal to 0, we find that Rdy must equal Rcy. We will call this equation 8. Lastly, we will sum our moments about point C and set this equal to 0. We see Rdx is going to act on a moment arm of 0.5 meters times a tangent of 28 degrees, whereas Rdy will counteract this when acting on a moment arm of 0.5 meters. Thus, we'll cast equation 9 as 0.5 meters times a tangent of 28 degrees times Rdx is equal to 0.5 meters times Rdy. Lastly, we will analyze member OBC. Recalling Newton's third law, RCX, RCY, RBX, and RBY will take directions opposite of what was previously specified. Thus, if we sum our forces in the x direction, set these equal to 0, we find we'd have ROX plus RBX plus RCX will be equal to 0. We'll call this equation 10. Summing our forces in the y direction, setting this equal to 0, we'll have ROY plus RBY plus RCY will also be equal to 0. We will call this equation 11. Lastly, we will sum our moments about point O and set this equal to 0. RCX is going to act on a moment arm of 2.5 meters, creating a clockwise rotation, whereas RBX will act on a moment arm of 1.75 meters, creating a clockwise rotation, and we'll have a reactionary moment M sub O, creating a clockwise rotation. This will create a net 0 Newton meter couple acting on our system. We will call this equation 12. We can cast these equations 1 through 12 as is in MATLAB using our symbolics toolbox, and then we can simultaneously solve for each unknown. Casting equation 1 in MATLAB, we will denote our symbols REX and RDX. Equation 1 will take the form REX plus RDX is equal to 0. Equation 2 is the summation of forces in our y direction, and we will cast the symbols RDY and REY. Equation 2 will take the form RDY plus REY plus 900 is equal to 0. Lastly, equation 3, being our summation of moments about point E, can be cast as equation 3 is equal to 0.2 times 900 is equal to 0.75 times RDX. Proceeding to equation 4, where we sum the forces in the x direction for member AB, we will define the symbol RBX, and equation 4 takes the form RBX is equal to REX. Equation 5 is the summation of forces in the y direction for member ABE, and we will define our symbol RBY and F. Equation 5 takes the form RBY plus F is equal to REY. Equation 6, which is the summation of moments about point B for member ABE, will be cast as equation 6 is equal to 0.5 times REY plus 0.470 times F is equal to 0.266 times REX. Equation 7, which is the summation of forces in the x direction for member CD, allows us to cast the symbol RCX, and equation 7 takes the form RDX is equal to RCX. Equation 8 was the summation of forces in the y direction for member CD, and we will define the symbol RCY, which allows us to cast equation 8 as RDY is equal to RCY. Equation 9 was the summation of moments about point C for member CD. We will cast equation 9 as 0.5 times tan D of 28 times RDX is equal to 0.5 times RDY. Equation 10 was the summation of forces in the x direction for member OBC. We will define our symbol ROX, and equation 10 takes the form ROX plus RBX plus RCX is equal to 0. Equation 11 was the summation of forces in the y direction for member OBC, and we will define our symbol ROY, which allows us to cast equation 11 as ROY plus RBY plus RCY is equal to 0. Equation 12 is the summation of moments about point O for member OBC. We will define our symbol M sub O, which allows us to cast equation 12 as 2.5 times RCX plus 1.75 times RBX plus our reactionary moment M sub O is equal to 0. We will put our equations into a matrix, actually a vector, and the same with our variables. We will define our equation vector as equation 1 through 12. Our variable vector will contain all our unknowns: F, RDX, REX, RDY, REY, RBX, RBY, RCX, RCY, ROX, ROY, and M sub O. Now to solve our system of equations, we will use MATLAB's built-in solve command. We will define our solution variable by solving our equations for our variables. In doing such, we will construct a solution array, which is a structure, and we can call each field within our structure to pull out a solution. We can display our force by taking the double of our solution.f. We can also display our reactionary moment by calling the double of solution.mo. We can do the same for RBX, RBY, RCX, RCY, RDX, RDY, REX, REY, ROX, and ROY. In doing such, we obtain the following output. Our applied force to keep our basketball hoop up is 957.4 newtons. If we notice in our last line, ROY would be the sum of F and our applied load of 900 newtons on the hoop, or 1,857.4 newtons. ROX physically makes sense that there is no reactionary force in the x direction. The remainder of the values are going to tell us the forces acting on each of our members. Please be sure to check out our course canvas page for this MATLAB code.